So what we will do today is we'll look at mass and really mass balances. We won't do anything on energy balances, but we'll look at mass balances, reactor design. You hopefully have watched the videos before class. So what we will do is really some just group processing. I'm just going to, the material that we'll discuss is also in Chapter 4, Materials and Energy Balances, and that is online Kappa in the assigned readings folder. So on Monday, we worked through this problem here. I'm going to briefly discuss it, and then we'll go on to the next problem. So here we have a wastewater. It is treated before being discharged into a lagoon. So we've got some treatment. That wastewater then is discharged into a lagoon. The lagoon has a volume of 5,200 meters cubed. The flow rate from the wastewater treatment is 0.015 meters cubed per second. You're told that the lagoon has been operating for months and it has a steady state concentration of salt in the lagoon of 250 milligrams per liter. However, there's been a plan upset, and that has resulted in a sudden increase in the influent salt concentration. It's increased by a factor of 4. So Monday's class was asked to draw a picture of the system, show the control volume, the system boundary, flows in and out, state their assumptions, etc. So we discussed it after class, and what you see here is the image. So what we have, so we have a lagoon, and right here we have flow in to the lagoon, we have flow out. You're told the volume is constant, so if the volume is constant, flow in must equal flow out. If not, the volume would be increasing or decreasing. You're told it's at steady state, so the concentration leaving and the concentration in the lagoon are equivalent. So what we have here, okay, the assumption we have just made by that is that we have a completely mixed reactor, or a CSGR, and from that we can make this assumption that the concentration at any point in the lagoon is the same as the concentration leaving the lagoon. The salt is conservative. That means that there's no decay. So the next thing we did was we wrote a mass balance equation in words, which is simply that the change in mass with respect to time is equal to the mass rate in minus the mass rate out minus the mass rate of decay. Now we said that we were at steady state, so because we're at steady state, the change in mass with respect to time is equal to 0. And we can write mass rate in as m dot in minus m dot out to denote that this is a rate. And since we're told that the salt is conservative, there's no decay, and that mass rate is 0. So that means that the mass rate in equals the mass rate out, which is what you would expect. Now, there's a sudden increase in the influent concentration. The equation, and now when there's a sudden increase, you're no longer at steady state. So we can no longer write that the change in mass with respect to time is equal to 0. So now we do have a change in mass with respect to time. We can solve that equation, and this was the equation that was given. We start out at 250 milligrams per liter, that concentration is going to increase with time, okay, as shown here. And it will asymptote at 1,000 milligrams per liter. So when it finally reaches steady state again, now mass in equals mass out, but at a concentration of 1,000 milligrams per liter. Any questions about this problem? This is the same graph, except just plotted in Excel. The problem then asked that the plant operators were able to restore operation of the plant. That resulted in a decrease in the influent concentration back to 250 milligrams per liter. So we're starting here at 1,000, because this is where we just showed previously. Okay, now the influent concentration is suddenly 250 milligrams per liter, and we'll assume it's a sudden instantaneous decrease. And now, again, same equation applies. It's just now C naught is equal to 1,000 and C influent is equal to 250. And the concentration is going to decrease until it reaches 250. And then when it reaches steady state, the influent concentration, the effluent concentration would also be 250. Now this is true because there's no reaction. Okay. If there were a reaction, the effluent concentration, and there were decay, then the effluent concentration would be less than 250, and that would depend on the reaction rate constant. And this is just the plot, the blue line being that decrease that we just discussed. Okay, so the problem I'm going to have you work on in groups. Do we have anyone in the classroom? So we have an ocean outfall diffuser, and it's discharging treated wastewater into the Pacific Ocean at a distance of 5,000 meters from a public beach. So think of that as a pipeline. It is a pipeline with a diffuser at the end that is discharging wastewater. The wastewater discharge flow rate is 1,440 meters cubed per hour. The wastewater contains 10 to the 8 coliform bacteria per meter cubed. It enters this pipe think of it entering at the beach. When it enters the beach, you've got a concentration of 10 to the 8 coliform bacteria per meter cubed. This pipe that's carrying the wastewater is flowing full. It has a diameter of 2 meters, and you're told that the rate constant for the inactivation of this bacteria in the pipe is 0.32 inverse hours. Now, we're going to assume first order kinetics. So at first order kinetics, dc dt is equal to minus kc. So that's first order expression. Okay, so we have this pipe. Here's our beach. Wastewater is flowing. It's 10 to the 8 per meter cubed. Okay. You were asked, and I just basically drew much of the system. Okay. So you're asked to draw the diagram of the system, write a mass balance for the concentration of coliform in the pipe, state all your assumptions, and determine the concentration at the point of discharge. Okay, so there are 5 of you in the classroom. Okay, so Patrick, what I'm going to do then is all 5 of you can work together. What I'm going to do is I'm going to manually set up breakout rooms. so that, Patrick, you're going to be in a breakout room by yourself with the other 4 classmates. Okay. So whatever, just assume whatever number you are, but just all 5 of you work together. There's no reason not to do that. Okay. Now, the next part of this here, at the outfall, the wastewater mixes instantaneously with the ocean. So you can assume that, or model the ocean current as a pipe. So basically now you have 2 pipes, the confluence of 2 pipes, one with wastewater, one with pure water or ocean water. Okay. Now you'll need to model that. So think about what system you need, how are you going to model that? And then lastly, you'll model the water as it flows back. So there's basically 3 subsequent parts to this. Okay. Think about whether this is a plug flow system or a CSTR in your modeling effort. Now that we have everyone back, let's go through and process this. So we've written the diagram. So let's just start. We've got a pipe and water is flowing through that pipe. Now we said that we can write an equation, change in mass with respect to time is equal to the mass rate in minus the mass rate out minus the mass rate reacted. Now with a plug flow system, remember what we're doing is we're modeling movement in the reactor in a small parcel. So, and this parcel is moving down the pipe or down the reactor. So there's no mass enter this small parcel that we have here. There's no mass entering this parcel or leaving. The parcel is just simply moving down the reactor with time. So this would be time naught, time, we'll call it time 1, time 2, and it's simply moving. So in that case, because there's no mass entering or leaving, the mass in term is 0, mass out term is also 0, and the change in mass is equal to minus K reacted, and minus the mass reacted. If volume is constant, we can pull volume out. So we have d ct dt is minus, and we've got the rate constant, and our rate constant is dc dt is equal to minus kc. This volume term, the volume isn't changing. The mass reacted is, we need to multiply that by volume. So this is concentration. We have volume on both sides of the equation. Volume now cancels, and we have dc dt is equal to minus kc. So that is the equation we can use for modeling the change in concentration of any chemical by change in microbial as it moves down the pipe. Now we said the pipe was flowing full. So since the pipe is flowing full, the area of the pipe is equal to 3.1415 meters squared. The velocity is simply Q over A, and that is 1,440 meters cubed per hour. I apologize for all these extra lines today. Divided by 3.1415 meters squared, and that is equal to 458.4 meters per hour. Since the distance is equal to 5,000 meters, the time that it takes for that parcel to traverse the pipe from the beginning to the end is simply 5,000 meters divided by 458.4 meters per hour, or 10.9 hours. And if we integrate this expression here from C0 to C and from time 0 to time t, we obtain ln of C over C naught is equal to minus KT. We're given K. We can also write this as C naught, sorry, C equals C naught e to the minus KT. So we can write it either way. And then C is equal to 10 to the 8 minus 0.32 inverse hours, which is given, times the 10.9 hours, and that is equal to 3.05 times 10 to the 6 bacteria per meter cubed. Typically, we would refer to as colony forming organisms, and it's usually referred to as CFU, colony forming units. The next part of the problem, now you have the pipe here, water's entering. We're going to model the ocean current as another pipe. These two come together, and we'll model this as a CSTR. Two pipes coming together, we have mixing at the confluence of those two pipes. So we'll model that as a CSTR. So we have now Q in here is equal to 1440 meters cubed per hour. C of the pipe is what we just calculated. We have the ocean, Q, the ocean is 2.0 times 10 to the 5 meters cubed per hour. And the concentration in the ocean we've said is 0. So we'll assume a CSTR. We'll assume that we're at steady state, so the change in mass with respect to time is equal to 0. We'll assume we have, spell instantaneous mixing, and we have no decay. So in that case, we have the change in mass with respect to time is equal to 0. We have the mass rate in. We have two mass rate in. So we have prime. So we have mass rate in from the ocean, and we have the mass rate leaving. And this is what's going back to the beach. And this is equal to 1440 meters cubed per hour times the 3.05 times 10 to the 6 CFU per meter cubed plus 2 times 10 to the 5 times 0. And that is equal to the sum of the two flows. So the 1440 plus 2 times 10 to the 5. And we're looking, we'll call it C out. So that pipe going back to the ocean. And that is equal to 2.18 times 10 to the 4 CFU per meter cubed. Okay, so that's the concentration in this mix before it moves back to the ocean. This last part we have now, so we've got this mix here, and now the water is moving back to the beach. And we're going to model this again as if it were a pipe. So again, we have plug flow. And the time that it takes, still 5,000 meters, so that didn't change. And the time that it takes is 5,000 meters divided by 1,000 meters per hour. It's velocity here. So that is 5 hours. And again, we have C equals C naught e to the minus KT. In this case, T, water's probably colder, so the decay rate is slower. And this is just equal to the 2.18 that we just calculated times negative 0.2 inverse hours times 5 hours. And that is about 8,000 CFU per meter cubed. Okay,